Welcome back to part 4 on complex zeros. We are on our last example. Example 5 says find all the zeros of r of x equal to x to the 5th plus x to the 3rd plus 2x squared minus 12x plus 8, and write it in factored form. In our study of polynomials, we've found several different methods for identifying where the zeros are. One of those ways of identifying the zeros is by plugging it into your calculator and graphing it and seeing where the x-intercepts exist, which is what I'm going to do now. I have the polynomial r of x input into my calculator, and now I'll graph it. It appears that I have a 0 at -2 and at 1. It also looks like it bounces at 1, so that would mean my multiplicity is 2 or more. So I'm going to change my window so that it's only from like -3 to 3, just to double check those values. And as I zoom in, I can see that yes, it does look like it crosses over at -2 and it does bounce at 1. So I'm going to use -2 and 1 as the two test values and show that if my remainder is 0, it is indeed a factor in the polynomial. So I'll try -2 first. Using synthetic division, I can't forget to put a 0x to the 4th in there. That will give me 1, 0, 1, 2, -12, and 8. Dropping my 1 down, I will have -2 times 1 is -2, 0 plus -2 is -2, -2 times -2 is 4, 1 plus 4 is 5, -2 times 5 is -10, 2 plus -10 is -8, -2 times -8 is +16, -12 plus 16 is +4, -2 times 4 is -8, and indeed I do get a 0 at the end. Since my remainder is 0, that tells me that -2 is a factor of r of x. So down here, r of x can be now written as x plus 2, my binomial factor with -2 as our 0, times the remainder here, which is 4, -8x, 5x squared, -2x cubed, and x to the 4th. Now I need to keep factoring the remainder. So I have to factor it further. So this is where I recycle my remainder. So now I'm going to show that 1 is a factor or a 0 of the polynomial r of x. Dropping 1 down, I get 1. 1 times 1 is 1. -2 plus 1 is -1. 1 times -1 is -1. 5 plus -1 is 4. 1 times 4 is 4. -8 plus 4 is -4. 1 times -4 is -4. 4 plus -4 is 0. I've shown that 1 is indeed a 0 of the polynomial. So now I'm going to take this whole piece of factor that I had left, and I'm going to replace it with x minus 1. That's the 0 that I just showed exists. And then the remainder, -4 plus 4x minus x squared plus x to the 3rd. And now I'm going to, since my multiplicity, remember on my calculator when I graphed this, I noticed that the multiplicity looked like it was 2 at the 0 of 1. I'm going to now try factoring out a 1 again. So I'm recycling. Dropping the 1 down. 1 times 1 is 1. Negative 1 plus 1 is 0. 1 times 0 is 0. 4 plus 0 is 4. 1 times 4 is 4. And negative 4 plus 4 is 0. So once again, I have shown that I have another root at 1. This shows multiplicity 2. So I'm going to put a 2 on my x minus 1 binomial factor. I'm also going to erase what I had as my remainder and rewrite this as x squared plus 4. Now I know just by looking at this that this is going to give me complex zeros. Setting those last factors equal to 0, x squared plus 4 equals 0, gives me x squared equals negative 4. When I solve for x, I will have to take the square root of both sides. Taking the square root of both sides gives me x equals plus or minus 2i. Since these are both complex zeros, I know what they are. They're at plus or minus 2i, but I'm going to leave it as a quadratic. So the only time you would list this as all the factors would be if it said factor completely, in which case you would write it as r of x equals x plus 2 times x minus 1 squared times x plus 2i times x minus 2i. Usually textbooks ask for just the whole integer values without the imaginary or complex portions showing, but it just depends on how the question is worded.